We were looking at examples of homomorph homomorphisms. We'll continue with that. Consider the group of real n by n matrices that are invertible. Under the operation matrix multiplication, we'll define the homomorphism phi from GLN of R to the set of the group of non-zero real numbers under multiplication. Given a matrix A in GLN of R, phi of A is the determinant of it. Is phi a group homomorphism? Yes. Give me 1 minute, I have to take a call. Hello. Sorry. All right. You were saying? Yeah. Yes, but the volume is a bit low. Uh, I'm I don't know how from my side if I am able to increase the volume. Yes, now it is better. Okay. So this determinant homomorphism, a determinant function is a homomorphism from the set of invertible square matrices to the non-zero real numbers. And this will come up later also. Next example is let G be any group fix an element A in G. So now the homomorphism is from the set of integers to the group G, and it is given by for any integer n, phi of n is Na. So earlier we had a homomorphism that um, that sent phi of A to Na, where n was fixed. This is a different homomorphism where you are sending an integer to phi of n to n is sent to Na, and A is what is fixed. So n varies. Is this a homomorphism? It is addition in integers because in integers multiplication would not give a group. So most of the time when I say integers, it is addition operation only. Group G can be any group. You can take multiplication as the operation. Or okay, instead of Na, then I'll write A power n. If n is positive, this is A times this. Then if n is negative, it will be A inverse into like this. And I will take A power n as the homomorphism. So is this a homomorphism? So this is a homomorphism. The next example is fix a group G which is abelian. Phi is here both the domain and codomain are the same group. It is a mapping from G to G. And given an element A in G, phi of A is A square or A times A. Is phi a group homomorphism? Phi of AB would be AB whole square. Since G is abelian, we can write it as A square B square. So then it will be phi of A, phi of A. So it is only true when G is abelian. If G is not in abelian group, we don't know whether it is. So actually, AB whole square is equal to A square B square is a necessary and sufficient condition for the group to be abelian. We saw in one of the problems. So this is only true in an abelian group. If it is not an abelian group, then phi is not a homomorphism from G to G. And the final example is the group of is again from the if the domain is the same as the codomain, but instead of function from a general group G to G, we'll consider a specific one. We'll take the function free from S3 to S3. You remember what S3 is, right? Hello, you are not clear. Yeah. So there we had six elements in S3, and each of them was a function. We had called them as F1 was the identity function, F2, F3, F4 were functions which swapped two elements and fixed the third element. F5 and F6 were functions which changed each of the elements, 1, 2, and 3. And each of these F5s was a function from the set 1, 2, 3 to the set 1, 2, 3. Now we define, now phi is a function on the set of functions. We'll define f phi of fi to be fi square, which is So here we said that G has to be abelian. Since S3 is not abelian, this should not be a group homomorphism. This example is to show that, just to give an example, that if it is not abelian, phi of A is equal to A square is not a group homomorphism. Now, if you check, you take F2 and F3. F2 was the function which fixed, it sent 1 to 1, 2 to 3, and 3 to 2. F3 was the function which sent 1 to 3, or maybe it was different, but we'll take this as F2 and F3 for this example at least. And Fy was the function which sent 1 to 2, 2 to 3, 3 to 1. F6 sent 1 to 3, 2 to 1, and 3 to 2. If you take phi of F2, F3, so here it's actually the composition. F2 composed with F3 is F5. Or is it? So F2 composed with F3 will be. I'm not sure if this is F2 or whether this we called F2 in the example in the beginning, that when I was giving examples of groups. I'll just check that once to stay consistent. No, this was actually, I'm trying to stay consistent with the previous notation that I had given. So F2 was the function which sent 1 to 2 and 2 to 1 and fixed 3. So it sent 3 to 3. Now F2 composed with F3 is the function F6. Phi of F6 is F6 times F6, which is F5. So here the times is also function composition because the homomorphism is from S3 to S3, and both are S3, so the operation is simply function composition within and here outside also. But if we check phi of F2 composed with phi of F3, you will get F2 squared composed with F3 square. This is nothing but F1 composed with F1, which is F1. So as you can see, phi of F2 composed with F3 is not equal to phi of F2 composed with phi of F3. So to identify whether function is a group homomorphism or not, I'll give a necessary condition. That is a condition which needs to be true if the group is a homomorphism, but it's not a sufficient condition. That is, if it has this condition, it might or might not be a group homomorphism. And the proposition is this: let phi be a group homomorphism from the group G to group G prime. Then the following two conditions are necessary. The image of the identity element in G must be the identity element in G prime. And if A is an element of G, then the image of the inverse of A must be the inverse of image of A. Can you prove this? Hello? Okay, that is okay for first part. For the second part, okay. Now if we go to lecture 7, the final example, we had phi from Z to 1 comma minus 1, and Phi of A was minus 1 if A is even, 1 if A is odd. So we can see that since 1 is the identity element in Z, it should be sent to the identity element in 1 comma minus 1. But that does not happen here. Sorry, it does happen here. Uh, then if1 must have been. Sorry. 0 is the identity element in Z, not 1. Because Z is a group under addition. So the identity element is 0. And the image of 0 is, since 0 is even, it is minus 1. But 1 is the identity element of 1 comma minus 1. So, yes, yeah. If it is a homomorphism, it must fulfill the condition. So you can take the contrapositive is also true. That is, if the condition is not satisfied, it is not a homomorphism. But if the condition is satisfied, we can't say whether it is a homomorphism or not. Yeah. So here the condition is not satisfied because the identity 0 is mapped to minus 1, which is not the identity in 1 comma minus 1. So we can say that this phi in example 3 is not a homomorphism. But we can't go to example 2 and say that the identity 0 is mapped to 1 in example 2 because 0 is even. And that would not be enough to say that phi is a homomorphism. To show it is a homomorphism, we will have to prove that phi of A plus B is equal to phi of A, phi of B in this case. So it's on this proposition is only useful to check whether something is not a homomorphism, but we can't prove that something is a homomorphism with that. So it is more like a simple test that you might do before trying to prove some function is a homomorphism. Instead of doing in general and then later finding out that P is not a homomorphism, you can check whether the identity is being sent to the identity first. If it is not true, directly you can say it is not a homomorphism, but if it can go ahead with the proof. Now, once we have this homomorphism, there are two important subgroups associated with the group homomorphism. Let phi from G to G prime be a homomorphism. I'll simply call it a homomorphism instead of group homomorphism because in this course we are only dealing with groups. So there won't be any confusion at least. But then when you go to rings, there will be ring homomorphisms which have an additional condition. Since we are not studying rings here, I'll just call it a homomorphism. So let phi from G to G prime be a homomorphism. We'll define the kernel of phi. denoted by kernel of phi, or sometimes I might write ker phi without the brackets. This is defined as the set of all elements in the domain, that is, set of all A in G, such that their image phi of A is the identity element of the codomain E of G prime. Since it is a set of elements from G, this is a subset of G. The image of phi, you can write it as image of phi like this, or I might drop the brackets, or I might write using capital, but I mean the same thing in all these notations. This is defined as all the images. So you take all the elements in G, find their image in G prime, find phi of A, and put all the phi of A together. These are all elements in G prime, so this will be a subset of G prime. Might be equal to G prime, or it might be a proper subset. Once we have those definitions, we have the following proposition. This kernel of phi is a subgroup of G, and the image of phi is a subgroup of G prime, where phi is a homomorphism from J to G prime. Can you prove this? Yes. Yes, we have to, this is to prove subgroup, we have to show closure and inverse, both. We want to show A star B is also in the kernel, and A star B will be in the kernel if what is the condition by definition. You can do one step test also. We had If you want to show AB inverse is in the kernel is a set of elements that are mapped to identity, right? So you have to show that phi of AB inverse is the identity. Then AB inverse will be in the kernel. Symbol for subgroup that we are using is this, less than or equal to. Okay, that is part one. We showed that kernel is a subgroup of G. Then we have to show that image is a subgroup of C. Image is a subgroup of G prime. Sorry. Yes. P of EG is EG prime. Therefore, EG prime is in image of P. It might be easier to show them separately, closure and inverse. Or if you want, you can show it in one shot. And since X and Y are in G, then G is a group, XY is in G. So AB is in the image. So image of E is closed. Then you have to show that A inverse is in the image. A inverse is P of X inverse. And if X is in G, X inverse is in G. So A inverse is the image of X inverse. That would mean that A inverse is in the image of P. So image of P is the okay. We started homomorphisms in lecture 7. Or did we start in lecture 6? No, we started yesterday only. Yeah. So we'll check the kernel and the image for the homomorphisms that we have seen till now. Yes, by definition. But you can, for any subgroup, you can always uh, construct a homomorphism such that the subgroup is a kernel. So we define a kernel only for a homomorphism. Given a homomorphism, you have the kernel of the homomorphism, curve phi. That's why we have written it as a function of phi. That's why you written it. This is more like that's where this notation is from. So curve of phi, so it's more of a function of phi. So for different phi, you will get different kernels. Similarly with image also. But the thing is, since kernel is a subgroup, right? So suppose you have a group and you have a subgroup of that group, then you can define a homomorphism in such a way that that subgroup, whatever subgroup you pick, is the kernel of some that homomorphism. You can define a you can define a homomorphism in that way. We'll see that in later classes. What I mean to say is that even though a kernel is only defined once you have a homomorphism, you can actually try to go the other way. It is possible. Given a subgroup of some group, you can define phi such that whatever subgroup it is, that will be equal to kernel of phi. So here in this example, phi from z to z, we fix an integer n, and then we take phi of any integer a is simply n times a. And just to make it clear that we are still dealing with addition in both the groups, I explained n times a is a plus a plus a plus a. So we're actually adding. Now, what will be the kernel of this homomorphism? Yeah, if a itself is zero, then all its multiples, regardless of what n is, it will be zero. But if it's any other integer, its multiple with a non-zero integer, product of two non-zero integers will be non-zero. And here, yeah, this was a positive integer. So n is not zero. That means only possibility for NA to be zero is A. A is also zero. And zero is the identity element. Other way to look at this, yeah, zero has to be there. That is true because zero is the identity element of Z. But that is the only element. Then the image in this case is It's the image of A is NA, right? So it's A. No, how will you get the entire thing? You can't even get zero, no? Unless A is zero. No, you're not allowed to take whatever value for n. If n is equal to 1, then yes, it is z. Yeah, you'd have to write in terms of n in general. In general, this is just A is any integer, so you're actually taking multiples of n. That is denoted by nz, all multiples of n. So if n is equal to 1, it's all multiples of 1, which is the set of integers itself. If n is equal to 2, it's all multiples of 2. If n is equal to 3, it's all multiples of 3. So in terms of n, you can write it as nz, all multiples of n. This is simply notation for multiples of n, the sense that you multiply each element of z by that number. Then this will be the set minus 3 and minus 2n. The next example, yeah, it was this. Here, what is the kernel? Yeah. No, it's just evens. No, there's no addition here, right? Kernel of E is simply the set of elements which are mapped to the identity in G prime. Yeah, there is no addition. So only even numbers are mapped to 1, and 1 is the identity of G prime. So this is simply the set of even numbers. You can write this as 2z. Then the image is, what is the image? So this is one example in which the image is equal to the codomain. The image is G prime. Here, if n is not 1, then the image is a subset of G prime in the first example. G prime is the set of integers. If n is not 1, then the image is not Z. So it is possible that the image is not equal to the codomain group. The next example was it was not a homomorphism. So that we stopped there in the last class. Then in today's class, this was the homomorphism we saw, the first one. Now, what is the kernel of this one? Oh, there are other things also which determinant one. See, this is set of all n by n matrices, not 2 by 2. And even in 2 by 2, there are different matrices which have, for example, this would also have determinant 1. So it doesn't have any structure, it's just a set of matrices with determinant 1. But it was also a group. It was called the special linear group. So this was the subgroup of the general linear group. This is the general linear group. So this was the set of all invertible n by n real matrices. That is, the determinant was not zero, it was the condition. All matrices with non-zero determinant are in GLN of R. And this is called the special linear group, where it's a set of all matrices with determinant 1. Since determinant is 1, they are also all they are also all invertible. But it is a subset, and it turns out that it is a subgroup of the set of all invertible matrices. So I am not sure if we showed that SLN of R is a subgroup of GLN of R, but this is one way to show it. So we have a homomorphism phi from GLN of R to R star, and the kernel of phi is the SLN of R. We know that kernel is the subgroup for every homomorphism phi. Kernel of phi is a subgroup of the domain G. So SLN of R is a subgroup of GLN of R. That's one way to prove it. What about the image? Yeah, it will be stuff. There are different ways to show that, but um, the matrix A0, pick any A in R star, then the matrix A0, 0, I n minus 1 has determinant A. That is this matrix A. With A as one of the diagonal entries and rest of the diagonal entries are 1 and rest of the elements are 0. This has the determinant equal to A. And since A belongs to R star, the determinant is not 0. So this matrix belongs to GLN of R, which is the domain. So for any A in R star, I have given a matrix whose image is that number A. So in the all of R star is the image of A, the image of phi. The next example was let G be any group, fix an element A in G, and phi of any integer n is A power n. Here, what is the kernel of phi? Uh, the order doesn't have to be n. Yeah. A raised to power n should be E, but there is no real structure. That's all we can say for this. Yeah, we will just have to leave it at that. We can at what we can say that it is. Yeah. So yeah, one what we can do is we know that since it's Z, there is something you can do. We can give the structure. So this is a subgroup of Z, right? And we showed in a previous lecture that all subgroups of Z are of the form dz for some element D. So if the subgroup is the trivial subgroup, then it is of the form 0z. And if the subgroup is not a trivial subgroup, then we suppose H is the subgroup, then we find the smallest element in H, smallest positive element, and H will be simply equal to that smallest element times Z. We know that a power 0 is equal to Eg. Thus, 0 belongs to the kernel. And 0 is also the identity element in Z. So it is mapped to the identity element in G, and thus 0 belongs to the kernel. That's also another way of putting it. If kernel of P is simply, if it has only 0 in it, then kernel of P is a set 0Z, all multiples of 0, all integer multiples of 0, which is simply the set containing only 0. If kernel of P is not equal to this trivial subgroup, then kernel of P is equal to dz, where d is the smallest positive integer in kernel of P. What is the smallest positive integer in kernel of P? Here a is fixed. That would be the smallest positive integer such that a power n is equal to e. Now what is that? Oh, we have a name for that. We have a name. The smallest positive integer such that a power n is equal to e. We have a name for it. We call it something. What is it? We have defined it as some quantity. Yeah, so that is the order. So if kernel of phi is simply the trivial subgroup, then it's just 0, it's z. Otherwise, kernel of phi is dz, where d is the order of a. So you can write kernel of phi is order of a z. So it's all multiples of the order, all integer multiples of the order. Okay. So since it had so this has a structure like this because it is the domain is the set of integers, and all the subgroups of Z have this nice property that they are of the form dz. Either that or it is simply the zero subgroup. What about the image of P? Image of P is revolve Pn such that n is in the domain which is Z. Pn is a power n. What is this? Oh, even if it is finite, it won't be G. A is some arbitrary element of G. Yeah, what is this set? This set also had a notation and a name. For given A in G, set of all A power n, set of all powers of A. Yeah, so this is simply the subgroup generated by A. If G is cyclic and A is a generator of G, then this would be G itself. Otherwise, it is simply the subgroup generated by A. The next one was, oh, we already did this. For an abelian group, kernel of phi is set of all A in G such that A square is equal to E. But this doesn't tell us anything, just for an arbitrary group. We don't know what that is. So we'll just have to leave it at that. And image is a set of all A square such that A is in G. And this also we don't know what the group is. Could be different in different groups. So here there's no real structure. We'll see some more examples. Consider the mapping from R star to R star. Phi of x is the here is the absolute value of x. So not the order of x, because other than 1 and minus 1, all the other elements in R star have infinite order. So it doesn't make sense to define P of x that way. So P of x is the absolute value of x. What is the kernel here? First of all, is this a homomorphism? What is P of AB? So let A comma B belong to R star. P of AB is the absolute value of AB is equal to absolute value of A times absolute value of B. So it's equal to phi of A times phi of B. So it is a homomorphism. And also if A and B are not zero, AB is also not zero. Multiplication R star, right? Real numbers without zero. Images. Next, let R of x denote the group of all polynomials with real coefficients under polynomial addition. Let f prime or p prime be the derivative of p of x. Now p prime of x is also a polynomial in R of x. Yes, yes, derivative. 3x square plus 2 p of x is this, then p prime of x is derivative 6x. That will also be a polynomial in x with real coefficients. P of x is simply the constant, then p derivative is 0. Both belong to R of x. Is this a homomorphism? Okay, but before all that, first, what is the identity element of R of x under addition? Yes, 0 is the identity. And the inverse of P of x is simply minus P of x. Okay, then if we have two polynomials P and Q, P of P plus Q is the derivative d by dx of P plus Q. Yeah, by some rule, it's the sum of the derivatives. So that is simply P of x plus P of Q of x. So it is a homomorphism. What is the kernel of the homomorphism? Yeah, set of all C, C in R. Or you can simply write R itself. All the constant polynomials. What about the image? Yeah, you can get any polynomial as a derivative of some other polynomial by integrating. Okay. Then consider phi from Z to Zn, defined by phi of an integer m is m mod n. Is this a homomorphism? That will become confusing because we are using Zn here. Yeah, we can take L and M maybe. This will be P of L plus P of N. Here, this is also mod n addition. Here also it's mod n addition. Here it is normal addition because it is from Z to Zn. So it is a homomorphism. What is the kernel of the homomorphism? it's all multiples of n, or you can say it's nz. And you can also write this as the subgroup generated by n, because subgroup generated by n will contain n plus n, n plus n plus n, etc. It will contain 0 times n, which is 0. It will contain minus n plus minus n, which is minus 2n, etc. So you can also write it that way. Next, consider image would just be Zn. Consider phi from R to R. So it's from R to R, not R star. So it is under addition. Now P of x is equal to x square. Is this a homomorphism? Can it be multiplication? Yeah, so operation is addition. Yeah, so in general it's not equal to phi of a plus phi of b. So this would not be a homomorphism. But phi of x is equal to x square would be a homomorphism from R star to R star. We saw phi of a is equal to a square. For an abelian group, it was a under multiplication, it was a group homomorphism. Since R star is abelian, phi of x is equal to x square would be a group homomorphism from R star to R star, where the operation is multiplication. Under addition, the same function is not a homomorphism. So, what I want to show here is that simply giving phi as a phi as a function is not enough. The um, the domain and codomain, the operation of the domain and codomain is also important. So the same function might not be a homomorphism when you take it as a function from two different groups. Next, we'll look at some properties of homomorphism. So I only prepared up to this part. Next part I will do, and if I skip something, I will cover it in the next week's lecture. Yes, but then I'll have to cut down on group. But since only you are attending, I can do that. Yes, rings, ideals, and fields. Okay, I can skip some topics in groups and do that. Wait. I'll uh, I'll cover some. I'll record a video on cyclic groups and I'll put it on the YouTube channel. You can watch it in your spare time and ask me if you have any doubts. Because I skipped one lecture. I missed one lecture last week, right? So I haven't recorded it yet. I will record it and post it. So I'll record that and do some problems because that thing might not be, I don't know how useful that will be. The thing is, that is all very inward. So if I, so it is actually just not possible to cover groups, rings, and fields in the same course. So I'll have to make some additional videos for topics I have left out. Yeah. Or we can, one thing we can do is, uh, I'll finish all the topics that you want. I'll finish rings, ideal fields, and then if you have leftover lectures, we complete it ahead of schedule, then we can come back to this. That is also possible. Okay. Okay. Then before we leave, I'll write the properties. I'll give the proof in the next class.